All right, let's talk about question 6. So now we have this device called RIP loads, and we have this circuit where three components are being parallel to each other with the voltage across their parallel nodes being VAB. Now part A asks that suppose we apply this test voltage VAB to the device, how much power will this device, which is this box of three components, use? So this device refers to the three components. And to measure the power of something, we must first know how to calculate power. In the basic sense, P is equal to IV, but we can further complicate that with Ohm's law by saying that P equals IV is also equal to V squared over R, given that I is equal to V over R. Okay, and we also know that this square box is a component that consumes a constant amount of power, that is P. So the total power would be equal to P plus P being a constant here, which is the power that the box takes. Let's write this clearer. Plus, and then I'm going to calculate the power that this current source consumes, but then I also know that P is equal to IV, so this should be equal to the current passing through the current source, which is the current that supplies, times VAB, which is the voltage across it. So this is from the current source. And last but not least, the resistor must also dissipate power, and we can calculate this as V squared over R. And this R is given by, its resistance given by R value, and so this power is from the resistor. And then we get the sum power of these components, or the total power that this device used, to be this algebraic expression. So now let's move on to the second part of the question. Usually the values of RIP are not known ahead of time, so we need to estimate them using some sort of way. And in this case, it is revealed that this way is called least squares. So what is the minimum number of values of VAB we could measure to generate a least squares estimate? So let's first look at the system that we're trying to deal with. First of all, each measurement of VAB grants one equation, or grants one measurement, which is one row of the total matrix. And the system being AX is equal to B, where X stands for the value we're trying to estimate, which will be R and P. And we also know that this system has three unknowns, which means X will be a three-dimensional vector, and that will mean that A must have three columns. And last but not least, A must be, or must have, linearly independent columns, so that the system's A will be invertible, and so will ATA B. And in that way, we can actually, only in that way, we can actually generate a least squares equation for an estimate for X hat. So A must have linearly independent columns. Okay, but for A to have linearly independent columns, especially three linearly independent columns, each column must have more than or equal to three elements. Because if I have, for any two-dimensional vector I have, it will always end up being linearly dependent. So I need at least three elements in each column so that it has the chance to be linearly independent. Okay, which means we need three rows, because each element takes a row in the column. So combining this point with the first point, I will need three measurements, or at least three measurements of VAB, such that A is still a linearly independent matrix. So now that we have faced part 2, we just have to go through part 3, which is part C. So we are now given this equation that is I is equal to k0 plus 1 over v times k1, where k0 and k1 are constants that we don't know and want to estimate, and then we're given this series of estimation with I and v. We will now need to try estimating k0 and k1 using least squares algorithm. So in every single least squares problem, the first step will be trying to formulate the problem, which means we have to come up with a matrix vector system. And in this way, we do know that for any measurement, let's say I1 and V1, or actually, for any measurements pair of I and V, the matrix vector equation of them looks something like this. Such that k0 times 1 plus k1 over v1 is equal to I1, for v1 and I1 being a pair of measurements. So in other words, if I expand this matrix to have multiple rows, which stands for multiple measurements, and so as for the measurements of currents, I can have a matrix vector multiplication system that looks like this. And again, we have k0 and k1 being at the position of the parameters being estimated. And last but not least, we have the right vector to be I1, I2, and I3, so that the pair of measurements match. So now we have formulated this least squares problem with the matrix vector system. We just need to first fill in the actual values of the matrices and then use the least squares equation to figure out what k0 and k1 actually is. So since we have went through the conceptual parts of this least squares problem, we just have to go through the mechanical maths of it. So first, let me fill in the measurements that we got. So first I'm going to fill in the constants and the unknown parameters because they will not change. So the set of currents I got were -1 amps, 1 amps, and 9 amps. And the set of voltages I got were -1/3, 0.5, and 1. But we need the reciprocals of them, so it will then be -3, -2, and 1. Or actually -3, 2, and 1, since the 0.5 is positive. Okay. And last but not least, we need to change the equal sign here to approximate sign, because we are getting the best estimate of k0, k1, not the actual values of it, or not the actual precise solutions for them, at least. So that being said, we now have our matrix vector expression, and we know that for such a matrix, we can call it as AK is equal to B, and the best estimation of K is equal to A transpose A inverse A transpose B, which is equal to a matrix multiplication that looks like something like this. 1, -3, 1, 2, 1, 1, and I need the inverse of this, which will actually take some time to get. And then I also have A transpose, which is 1, 1, 1, -3, 2, 1. And then I have, last but not least, the B vector, which contains the currents. So -1, 1, 9. I'm going to use the rules of matrix multiplication and deal with these matrices group by group. So I'm going to deal with it group by group in the order of this, so I can finish as much mechanical math in each step as possible. So first I'm going to deal with the first parentheses, which requires me to get an inverse of something. That something being the product of A transpose A, but I first need to get the A transpose A components. So I'm going to do the math and discover that the matrix looks something like this, and I need the inverse of it, which we'll find fairly soon. Meanwhile, I will also take care of the second parentheses so that I can deal with this math and finish it earlier. I get that through the matrix multiplication, the vector looks something to the lines of this. Okay, so now I just need to find the inverse of 3, 0, 0, 14, which is a left-hand side matrix. And the way I can do this is use the general formula for inverses, which means that 3, 0, 0, 14 inverse is equal to, let's write out the general formula first, and then we can just apply it later. So the general formula looks something like this. BC, D, negative B, negative CA. So applying this formula, which we derived in lecture or in worksheet or in homework, we can dictate that the matrix, the inverse matrix of the matrix I have above, which is 3, 0, 0, 14, looks something like this. Which then grants me this matrix that is 1/3, 0, 0, and 1/14. So I am dealing with a matrix multiplication that I'm going to write on the left so that I can find the best estimate of K0 and K1. And last but not least, that ends up being 3 and 1. So K0 is around equal to 3, or that the best estimate of K0 is 3, and the best estimate of K1 is equal to 1. So via the least squares algorithm, we have solved this question.